Welcome back, everybody, to more of the 2003 Hypatia paper. We're taking a look at question number 3, and it's got no parts to it, so hopefully it'll be a nice, clean, crisp question. In the diagram, the sphere has a diameter of 10 centimeters. Also, the right circular cone, so it's a circular base, it's sort of right angle, so the point here is directly above the center, all the way through. The circular cone has a height of 10 centimeters, and its base has a diameter of 10 centimeters. Okay. The sphere and the cone sit on a horizontal surface. If a horizontal plane, so something parallel to the table they're on, I guess, cuts both the sphere and the cone, the cross sections will both be circles, as shown. Okay. Find the height of the horizontal plane, so how far above the base it is, that gives the circular cross sections of the sphere and cone of equal area. So we're looking for basically at what height does this plane cut it into circles that are the exact same. Because the only thing that's going to tell what size the area of the circles are is the radius. So they'll need the same radius. So let's draw ourselves pictures of the cone. That is an awful cone. Let's give it another try. Pretty good. It's a little too high up on the page, but that's not bad. Okay. So the point of the cone sits directly above its center. And so it'll be above the center of the sliced circle, and we're up a height of h. And we know the base has a diameter of 10 centimeters. We're just taking a look at the cone right now. We'll take a look at the sphere in a little while. I want to better understand what a sliced circle looks like. Can I figure out its radius or area in terms of the height? And then I'll do the same for the sphere. I'm not looking at them both together because that would likely overwhelm me or confuse me. I'm looking at the cone. I want to understand the cone and its circles, and then I'll move on to the sphere and understand its circles. Okay. So we know the overall height of the cone. We're told that that is also 10 centimeters. Okay. So the radius of the base, if the diameter is 10, the radius has got to be 5. Now, if I want to determine the area of this cut cone, the cone that appears when you cut the cone with the horizontal plane, I want to understand the radius here. And so I see so what you do is sort of look at it flat, and we notice that, hey, what we've got is a situation involving similar triangles. Right? We have a common angle up here, and because it's right angled and it's above the center, we're going to get two isosceles triangles. With a common angle here, we're going to have the same angles everywhere. So, this height is x, this height is 10 minus x, and we notice that the ratio of, you know what, we should probably give these things names, A, B, C, and D. So ABC is similar, not congruent, to ADE. And let's give these guys names F and G. So the ratio of lengths in these triangles is going to be constant. So the ratio of AC to AE is the same as the ratio of CB to ED, that sort of stuff. So what we can see is the ratio between their bases must be the same as the ratio between their heights. So BC over DE, so that's the two bases, should be the same as the ratio between the two heights, AF, AG. Well, we know what AG is, we know what AF is, H and 10 minus H, and we know what DE is. And that would mean that we know what, we can figure out what BC is. And BC is the diameter. So BC is DE AF for AG. Well, that's 10 for the base and 10 for the height of the whole cone. And then AF is 10 minus H. So BC is also 10 minus H. Fantastic. Okay. BC is the diameter of the small circle. So that circle has radius of 10 minus h over 2. 10 minus h is the diameter. You want the radius? You have it. Okay. So we know what the radius is, and using the radius we can figure out the area. So that gives us enough to better understand the cone. Now how about the sphere? The sphere is going to be a little trickier, both to draw. Yeah, it's kind of a lopsided sphere, but we'll roll with it. Now the problem is this height h at which the plane cuts. If h is below the halfway point, we'll get a circle below the halfway point. But if it's above, we sort of get a circle above the halfway point, and there's no nice linear term expression for the radius, like we have 10 minus h. It's not h squared, it's not square root of h, it's nothing like that. It's just a 10 minus h over 2, and that's nice and linear, and we can work with that. So, going to have to be a little more creative here. And it's likely going to depend on whether h is bigger than 5 or less than 5. So we have a center here, and the big circle has radius of 5. Okay? If we were to connect it up if we were to connect the center of the sphere to a diameter of our cut circle, what would we have? Well, center O, and we'll say A and B over here. So just as before with BC, we want AB is, or we have decided that AB is the diameter of the circle. So we want to understand the radius, we want to understand the area, we need to figure out what AB is. Okay? So, we know since A and B are actually points on the sphere, we're going to have these lengths of 5 here. Another thing, AB is going to be sort of a chord of the circle that we can see here. So we know O is going to be lying directly above AB, and it's going to hit at a perpendicular angle. Okay. So, what else can we say? Where are we getting some things? So, O sits exactly 5 above the base. Okay? Because the radius is 5, the height is 10. 10 divided by 2 is 5. So that's the height there. So we know that if h is less than or equal to 5, we'll give this guy named C. OC is 5 minus h. If, on the other hand, h is above 5, it turns out OC will be h minus 5. Okay? So ultimately what we could say, if we wanted to, for example, use absolute values, we could say OC is the absolute value of 5 minus h. Okay? Using that value, we have a Pythagorean triangle. OCA is right angled. So that means that OA squared, which is 5, is the same as OC squared plus AC squared. Okay? Well, OA is 5 squared, and OC, well, it can be 5 minus h, or it can be h minus 5, but it doesn't really matter, because once we square those, they become the same value. Plus AC squared. Okay? So you can check, if we were to use 5 minus h or h minus 5, either way, when we square it, we get the exact same thing. We get 25 minus 10h plus h squared. So it didn't really matter what h was here. So C squared, plus AC squared, not equals. AC is a radius. Well, we know the radius of the one circle, the circle coming from the cone. If we can figure out what AC is, we'll know the radius of the circle coming from the sphere. Okay. So if we rearrange these, the 25s are going to cancel each other out. And we're going to be left with 10h minus h squared is equal to AC squared. Okay. Now AC is a radius. I think I just said that. So the area of this circle coming from when we cut the sphere with the horizontal plane. So I could square root this expression and get a value for AC, but if I'm comparing areas, it's pi times the radius squared. Well, what's the radius? AC. So pi AC squared. So pi times 10h minus h squared. So the area of the cone circle, it's pi r squared. Well, what was the radius? 10 minus h over 2. So we have to square that. And we get pi 100 minus 20h plus h squared all over 4. We want the areas to be equal. Right? That's what the question's asking us for, right? The circular cross sections of equal area. So let's set the areas equal to one another. So pi times 10h minus h squared, the same as pi 100 minus 20h plus h squared all over 4. Well, the pi's are going to cancel each other out. And we can multiply through by this 4, bring them over to the other side. we'll get 40h minus 4h squared is the same as 100 minus 20h plus h squared. Okay? And now if we rearrange these things, if we group the h squareds and the h's together, we're going to get ourselves a quadratic equation. We'll have 5h squared minus 60h plus 100 is equal to 0. I notice I have a common factor of 5, so I can take that out. And we're left with h squared minus 12h plus 20 equals 0. Okay. Now I think, are there two numbers that multiply to give me 20 and add to give me negative 12? And indeed there are. So I know I can factor this as h minus 10 and h minus 2 equals 0. So the solutions are h equals 10 or h equals 2. Now, the way they have phrased it, can the height be 10? Because that would be at the very top where both circles sort of have radius 0. That single point on the top of the cone and the very tip of the sphere both have a radius of 0. So they're just going to be single points. Or a height of 2 above the base will also work. And then we'll have 4 here and then 5, 3, 4 here. A horizontal plane cuts both the sphere and the cone. The cross sections will be so. Find the height. I'm inclined to interpret it as you're cutting the sphere, you're not skimming the tops. And I would phrase that as such. I mean, 10 or 2 should be they're both valid if you interpret the question that way, but so we're cutting them, we're not skimming them, we're not grazing them, we're not just lying tangent to them. It's a tough call. The equations tell us 10 or 2, but if we read the question, you know, I'd say you can probably interpret it both ways, but we'll go with h equals 2 because that is a genuine cut through the cone and the sphere. Okay. So that was a nice whole question. No A's, no B's, nothing like that. And we took a look at them individually. We looked at the cone by itself and tried to better understand its circle in terms of radius or diameter or area. And we looked at the sphere. It was slightly more complicated. We might have been thrown by the absolute values that you could have. The fact that h could be above 5 or below 5, you might have split it into two cases, and that's fine. But ultimately, we got a better handle on the circle that comes from the sphere. And then we equated the two area formulas that we got, and we were able to rearrange those. And you could have used the quadratic formula. I like to factor a quadratic when I can, but if it's unfactorable, we could have had some, or not unfactorable, but not factorable with nice clean integers. We could have had a really weird height, like 3 root 3 or something. And at that point, quadratic formula much better to use. Okay. But as I said, you could probably make the case that the tip also works up here, but the real answer is a height of 2. And if you wanted to, what you could do is you could double check your answer by saying, okay, the height is 2. Let's actually go through those cone calculations again, knowing that my h is going to be 2, and figure out, well, what's the radius? What's the area of the circle? And then do the same thing with h equals 2 for all your work you did with the sphere, and realize that, yeah, these are going to give the same areas, and they are at the same height. So you can double check that if you have time, or, if you're a little frightened of question number 4, and that's okay. Every once in a while, question 4 comes along that frightens us all. So if you really want to devote yourself to questions 1, 2, and 3, you want to get them perfect before you do 5, one thing you can do is if you have a proposed answer, go back and check that it sort of jives with the arithmetic, that it all works out. Okay? But that's question number 3. Join me in the next video for question number 4 as we finish off the 2003 Hypatia. Thank you guys so much for watching.